Those are online. Are you able to see the screen?
Yes, sir.
So are we ready to get? Yeah. New chapter. I hope this chapter 5 only, no, in your textbook, because they deleted the first chapter. Does someone have your textbook? Oh, for you, they started volume 2, no? Okay. Yeah, solids. You have the first volume, no? The SAR book, no? So which chapter is that? 6 and botrukadala. 6 illa, appa 5 then. And the first chapter is deleted. Right. So shall we get started with this? Just a minute. What is the date today? 17, huh? Okay. So the topic we are going to discuss is, what is the name of it? It's called work, energy, and power, right? If you ask me, I consider this chapter to be the most important. It's not only for physics, rather it is for your chemistry also. Because wherever you are going to talk about, whether it is going to be about a physical characteristic or you're going to talk about a chemical reaction, the most important term that we need to understand is energy. Right? Because this word energy is not confined only to physics. Right? Did you learn about energy in your chemistry as well? Where did you learn it? So when you talk about an electron, there is something called as energy that is released in the form of electromagnetic waves when it is traveling from a higher orbit to a lower orbit. Similarly, we need to supply energy for it to travel from a lower orbit to higher orbit. So we are repeatedly using the word energy again and again. But the question is, where does the term energy come from? So for us to understand the term of energy, what is the most important thing to be understood? It is work. Right? So that is why if you look at this chapter, right, this chapter actually goes in this format. First, we'll try to understand what is work. What are the different kinds of work that can be done? By doing that work, what is the energy we are able to, what is the energy that we need to spend, or what is the energy we are able to extract out of that work, right? After that, we will calculate the rate at which we are able to do that work. The rate at which you are able to do work is what is called as power. So to put it simple, these three terms are interrelated. And most importantly, work and energy are always interrelated. You're able to understand? So if you do some work, you're going to extract energy. And for you to do some work, you need some energy. That is the whole idea, right? So having said this, what we will do is, all that I discussed is in an open perspective, in a layman perspective. I didn't get into the mathematical details or anything, right? So we understood for us to do some work, we need energy. By doing some work, we extract energy, right? Now, we will go in the format of understanding what is work first, then what is energy, then we look at what is power. So having said that, the first question that we need to understand is, what is work? Is there a definition to work that you can give? Right. So let's think of a simple logic. Let's say there is this magnet lying here. Okay, there is a magnet lying on my table. Let's say it's in my hand. I'm holding it. Am I doing any work? No, right? I'm just holding it. Maybe for this also I need some energy. If I'm weak, I cannot do it, right? But that is basic work done in terms of layman perspective. But what is work said to be done in terms of physics? So when can I say work is done? Yes, when I apply a force on that object and I cause some displacement to it. So now did I do some work? I held it, I lifted it, right? So from here to here, I applied some force and that force caused some displacement, right? The force caused displacement in which direction? In the direction of its application only. I was actually pulling it, right? I was trying to pull it. So when I try to pull it, force into this displacement called as work done. So for you to mathematically define work, what are the two important parameters that you need? You need to understand what is the force you're applying on an object, and that force is causing what displacement to that object in the direction of application of it. Okay, so that is like you see, there is no proper definition for work. Work is always said to be done, right? So work is said to be done. This is the most important thing. Will not give a direct definition to what is work. There is no definition. There is definition only for work done. Okay, work is said to be done whenever a force acts on an object and it moves the object through some distance in the direction of force. So you're applying a force on the object, that force should cause a displacement in the direction of its application. Okay, thus work is done on an object only if the following two conditions are satisfied. What should happen? A force needs to act on that object, and the second thing is the point of application of force moves in the direction of force, right? So what is the example? Example that you can think of is work is done when horse pulls a cart, an engine pulls a train, a man goes up the hill, right? All these are examples of work said to be done. Am I clear with that point? So just make a quick note of it. Right, yeah. Let me know once you're done. You're done? You just help me with this thing. So this question is there, no? Questions are there, no? So for the 11th question, I'll tell the answer, check if it is coming there. So where is the 11th point? Here. So what is the question? So what is the answer? 11th one, no? Velocity. CITY. Okay, next. The point of reference used to determine the, just give me 2 minutes, guys. I have small work. Just give me 2 minutes, okay? Yeah. What is it? The point of reference used to determine the motion of an object. Where is point number 1? Okay, it is a frame. Okay, next one. So second one, trajectory. Okay, next one. Speed of an object at any instant of time is? So where is 4? 4 is here. Instantaneous. Okay, next. So fifth one, where is it? That tells us the speed and motion. Where is it? Fifth one. Direction, velocity. Meter per second. TER/SECOND. Okay. Speed. Okay. Same direction, no? 9th one. Where is the 9th one? Yes. Same force, sir. Continues to move with the same, no, same force. Continues to move with the same force. Actually, it's same speed. SP. Okay. Give me a pen, no? Last one. Change in position with which one? Where is it? Yes. Change in position with respect to time. Huh? It's motion. That's fine. Only the 9th one is wrong, no? Okay, thank you. Bhaskar, ma'am sollu 9th one motto speed and matram sollu. 9th one motto speed. Yeah, thank you. Sorry guys, shall we continue? Yeah. No more work. So work done by a constant force, right? So we understood that. Yeah. So the next topic that we'll discuss is work done by a constant force. So we understood that for you to define work, right? Whenever you need the work to be done, what is important? Force and the displacement in the direction. So when you talk about the work done by a constant force, listen to this carefully. Let's say there is a block lying on a table like this of mass m. Okay. And the same block of mass m is lying like this. Okay. It's the same scenario. In the first scenario, what I'm doing is I'm applying a force in this direction, in the horizontal direction, right? So that the object has got displaced to this much value. Let's say there is a displacement of s that has got caused in the object due to this force. Then in this case, if I need to define the work provided, this force is a constant force. What is the meaning of it? Means if I start applying 5 Newton on this, I should apply the same 5 Newton throughout the journey, right? So work done will be equal to force into displacement. And this is what you would have learned in your lower grades. Am I right? Now we'll slightly extend it. What I'm going to do is I'm going to apply the same force, but this time not exactly horizontal to the surface, rather at an inclination with respect to the surface. So if I apply it with respect to, if I apply it at angle theta with respect to the horizontal, Then this f can be resolved into two components. What is it? It is f cos theta and it is f sin theta. Okay, so that the object is going to travel to this point, and let me say that this distance is going to be s. Okay, this distance is going to be s. This time, how are we going to define the work done? If you observe, in the previous case, the force was in the direction of displacement, so I wrote it as f into s. But this time, the force and displacement are not in the same direction. So I need to take the component of it, which is acting in the direction of displacement, and multiply it with displacement. So you should write it as f cos theta multiplied with s. So this gives rise to another definition and the most important definition of work done, which is f vector dot s vector. Because fs cos theta is basically the dot product between the force vector and the displacement vector. Am I clear with this? So it is given as the force vector dot displacement vector. Am I clear with this? So this is going to be the formula or mathematical equation, whatever you're going to call it as, for work done by which force? Constant force. Right. Now the next question that we need to answer is, when we say that we are defining the work done by a constant force like this, is there something called as work done by, what is the opposite of constant? Variable. Is there something called as variable force? If it is so, then how are we going to define the work done for it? Right. So for that. Oh, I didn't write it here, but yeah, I'll put the question as, what is the work done by a variable force? See, suppose the force is variable in nature. If the force is variable in nature, then the only difference is going to be, thing is, I could write this f into s because I know that this force is constant throughout the displacement. Whereas, if the same force comes out to be a variable, right, then you cannot define this formula for the whole journey. Rather, you can define this formula only for an instantaneously small journey. In the sense, what I will say is, this force is variable between the points A and point B. What is happening? It is variable between point A and point B, where the object has got displaced through the same displacement, let's say through the same displacement S. But I can treat this force as a constant for an infinitesimally small value. In the sense, this force is there. No, let's say this force, let's say you applied a force of 1 Newton at the first second. At 1.2 seconds, you changed it to 2 Newton. So what has happened? Between that 1 to 1.2, actually 1 to 1.2 itself is a very big number. Between 1 to, let's say, 0.000002. So between 1 to that 1.000002, how much was the force that you applied? You applied 1 Newton. So can I say for this small amount of time, was the force constant? Are you able to understand my point? Right. After that 1.00002, how many zeros are there? From there to 0.0003, you increased it to 1.2 Newton. So what can you say about 1.2 Newton? 1.2 was constant between that time interval, 2 and 3. Similarly, between 3 and 4, it will be a constant. So what I'm going to do is, I will break this whole S into infinitesimally small values. Infinitesimally in the sense, there are infinite small values that are going to exist between these two, out of which one of the values I will take it as ds. So that for this ds, the force is going to be a constant. Right? So for this ds, if the force is going to be constant, then how can you write this dw as? dw is equal to, I'm going to use this formula because the formula is known for a constant force. But this constant force F is acting for how much time or how much distance? It is acting only for a displacement of ds. So F into ds. Understand this. F into ds is going to give a very small amount of work done by this force for causing a displacement of ds. So that is why I borrowed this formula, I applied it here, but I applied only for that small journey. That is why the work done came out to be dw. It is not completely w. Right? It is not completely w. So when I want to find the value of W here, what I'm supposed to do is, so W will be equal to integral of F into ds from S1 to S2, and this will be the work done for the variable force. So in a given question, if the force is a constant force, then apply either of these two formulas. If it is a variable force, apply this formula and then integrate it. Is the point clear? Right? Did you understand why did I take that small value and then I integrated it? So just make a note of it. So the next topic that we'll discuss is nature of work done in different situations. The meaning of it is work done can be classified into three types. What are they? One is going to be positive, and the second is going to be negative, and the third is zero. Okay. So we understood that the formula of work done takes the dot product of force and displacement. We know that work done is equal to F vector dot S vector, right? So this can be written as F into S into cos theta. So in the first scenario, if I take the value of theta is equal to 0 degrees, then what is the work done going to be? So work done is going to be force into displacement. So work done will be force into displacement, which is going to be a positive value, right? Suppose I take the value of theta is equal to 180 degrees, then work done will be equal to force into displacement into cos 180, which is going to be minus F into S, which is going to be negative. Which is going to be negative. And third is, right? The third is, if I take the value of theta is equal to 90 degrees, then you can say work done is equal to F into S into cos of 90, that is going to be 0. Right? So here, let's take an example. If you look at an object of mass m, which is subjected to a force F, and the displacement is also caused in the same direction, then the work is said to be positive. Okay. So whenever there is a question, right, whenever we say work done, right, you should always ask a question of work is done by which force? Meaning, let's say I have an object of mass m lying so that I apply a force F on this object, and there is a frictional force acting in the opposite direction, and there is weight acting downwards and the normal reaction acting upwards. So this is going to be the structure of the free body diagram for this scenario, right? If I ask you, what is the work done by this force F? What will you say? So if I ask you, what is the work done by the force F, where it is causing a displacement in this direction, where the displacement is caused in this direction through a value of S. So what will be the work done by it? It will be F into S. See, don't get confused. It is not W into F. It is the work done by the force capital F. Similarly, if I ask you what is the work done by the frictional force, what will you say? It will be small f into S into, see, small f is in this direction, S is in this direction, into cos of 180. So this is going to be minus F into S. So work done by the frictional force in this scenario is going to be negative. What about the work done by mg? Mg is downward, displacement is this side into cos of 90, answer will be 0. Similarly, what is the work done by the normal force? What is the work done by the normal force? Normal is upward, displacement is rightward into cos of 90, answer is going to be 0. Are you able to understand all these points? Right? So, I hope you're able to connect both the dots. So within the same scenario, on the same object, there are 4 forces, but if you see, the work done by all the 4 forces are completely of different nature. Is that point clear? So that is why I always stress on the point. If somebody asks you a question, if there is a question saying, find the work done, the question is meaningless. What is the important question that you need to ask? What is the work done by which force? You should ask a question of which force are you talking about? For example, in this case, if I put a question saying find the work done, it doesn't make sense. Work done by 4 forces are there. You need to mention which force I'm talking about. So from here, I can ask a question. What is the work done by gravitational force? Tell me. What is the work done by mg? 0. What is the work done by normal? 0. What is the work done by friction? It is minus Fs. It's negative. Work done by the external forces, capital Fs, which is positive. Is that point clear? Right. So just make a note of. Those who are online, are you done copying it?
Yes.
Yes.
Okay.
Yes, sir.
Shall we proceed? Shall we proceed? Yeah. Done? So now let's solve some problems based on work done. So let's solve some problems based on work done. The first question is, a gardener pulls a lawn roller through a distance of 20 meter. So distance is 20 meter. If he applies a force of 20 kilogram weight in a direction inclined at 60 degrees with the ground. So force applied is how much? 20 kilogram weight. So whenever you have the force in terms of kilogram weight, how will you convert it to Newton? So you need to convert it to Newton as 20 into, you need to multiply it with 9.8. Okay, that is acceleration due to gravity. 20 into 9.8 is going to give you 98 into 2. It's going to give us 196 Newton. Did you understand this? Right. Now, the value of theta here is going to be 60 degrees. So there is a force that is inclined in this direction at an angle of 60 degrees with respect to the ground, with respect to the horizontal. Now, find the work done by him. So what is the work done? It's simple actually. Work done is equal to F into S into cos theta. So F is how much? 196 into S is 20 into cos of 60. Cos 60 is half. So this and this will get cancelled. 10. It will be 1960 Newton. So sorry, 1 minute. Correction. So 1960. Yeah, 1960 Newton meter. But generally, for work done, you don't write it as Newton meter, you write it as joule. Okay. Right. Let's proceed to the next question. So second question is, a person is holding a bucket by applying a force of 10 Newton. He moves a horizontal distance of 5 meter and then climbs up a vertical distance of 10 meter. Find the total work done by him. So let's try to understand this. So there is a bucket that is being held, right? There is a bucket that is being held with a force of 10 Newton, right? So he's holding it like this, right? In the first case, he's moving horizontally. Then he's climbing up and he climbs up a vertical distance of 10 meters. So tell me, when the force is upward, in the first scenario, how is the displacement? It is horizontal. So in the first case, that is through this horizontal distance of 5 meter, the force and displacement were perpendicular to each other. So in this case, what is going to be the work done? work done is going to be 0. So work done is going to be 0 when the person is moving horizontally. Whereas when the person is moving vertically, then force is upward and displacement is also upward. So if the force and displacement are in same direction, is the work done going to be positive or negative? Obviously positive, because the angle is 0, right? So from here, what can we conclude? Work done is going to be equal to, what is the force that is acting? 10 Newton. And what is the displacement cost? 10 meter. So 10 into 10 is going to be 100 joule is going to be the answer. So work done in the first case is 0, work done in the second case is 0. If you read the question, they're asking what is the total work done by him. So total work done is going to be 0 plus 100, which is still going to be 100 only. So why I mentioned this is, if at all there was a scenario where you had a non-zero value, you need to add it properly. Is the point clear? Right. So work done will be, total work done itself is 100 joule. Okay. So they started the solids chapter. Huh? Is it easy? How did you feel? Easy only, no? Or tough? Okay. Shall I proceed? Try to do this. So here the question says, a cyclist comes to skidding stop in 10 meter. What do I mean by that skidding stop? So generally the wheel of a cycle is going to rotate, right? But when brakes are applied strong enough, what will happen? It starts skidding, in the sense the tires stop rotating and they start sliding, right? That is what we call it as skidding. So for 10 meter, what was observed? The cycle was skidding. So during this process, what will happen is the wheel is there, no? The wheel would have had, this point would have had a continuous contact with the ground. See, if it is rotating, what would have happened is this point would have had for, let's say, 0.1 seconds, then this point would have come, then this point would have come. It would have gone in rotation. But when it is skidding, what will happen? This point is going to be in touch with the floor till that 10 meter is achieved. Are you able to visualize the situation? Question is, the force on the cycle due to the road is 200 Newton. So what is the force exerted by the road on the cycle? What force can it exert? Friction. So it will exert in this direction of how much value? 200 Newton. And how much is the displacement cost? Obviously, it is moving in the forward direction, 10 meter. Right. So what is going to be the work done by the friction? So how much work does read the question carefully. How much work does the road do on the cycle? Road in the sense friction does on the cycle. So what is the work done by the friction in this case? So W of F, work done by friction. So just to change this, no, what I'll do is, I'll just give you another notation for it. So what you can do is you can use the small f as a subscript. So WF is equal to, how do you write it? Small f into S into cos of 180 degrees. So what is small f? 200 into, what is the value of S? 10 into cos of 180 is -1. So it is going to be minus 2000 Newton meter, or it is going to be minus 2000 Joule. Am I clear? So work done by the road on the cycle is going to be minus 2000 Joule. Now, what is the next part of the question? How much work does the cycle do on the road? So what will be the answer? Work done by the cycle. How much is it supposed to be? See, work done by friction is minus 2000. Work done by cycle on the road should be plus 2000, no? This is where we need to stick to the basic of definition. What does work done say? It's not like you apply force alone. That force should cause a displacement. So the frictional force applied by the road on the cycle is causing a displacement of 10 meter. But the force applied by the cycle on the road, is it making the road move? The road is there only. So the force created by the wheel of the cycle is not sufficient enough to move the road. Hence, there is no work done by the force on the road. There is no work done by the cycle on the road. It is only the road that is doing the work on the cycle. So don't get confused. This is one common mistake that will happen. So work done by the cycle in this scenario is going to be 0 because there is no displacement at all. Are you convinced? Right? Shall I proceed? Shall I proceed? So the fourth question is, a force of F vector, actually this is F vector is equal to I cap plus 5j cap plus 7k cap acts on a particle that displaces it through a distance of S vector, which is 6i cap plus 9k cap. Calculate the work done if the force is in Newton and the displacement is in meter. So work done is equal to, we know the formula, no? It is F vector dot S vector. But you can ask me a question, sir. You told that F vector dot S vector is only for a constant force. Because for variable force, we use integral. So by looking at this value, or by looking at this expression of vector, how did I say it's a constant force? No, nowhere they told it's a dot product. So how will you come to a conclusion, or how will you make a decision saying that this is a constant force? By looking at the coefficients. If you look at the coefficient of force vector, what are they? They're just numbers, 1, 5, and 7. So hence, they are constants. Whereas, had the question been like this, F vector is equal to x square I cap plus 2x j cap plus x cube k cap. This x is a variable. This will become a variable force. So I hope you are able to understand. So this variable, this constant, as long as the force is constant, just go with the formula of F vector dot S vector. So when you solve this, what are you going to get? So you know how to do the dot product, right? So you'll multiply the corresponding coefficients of I, j, and k and add them. So 1 should be multiplied with 6 plus 5 should be multiplied with 0 because there is no j cap there. So 5 should be multiplied with 0 plus 7 should be multiplied with 9. So it is going to be 63 plus 6, which is going to be 69 joule. Right? So it is going to be 69 joule. Am I clear with that? Yes. See, this is the first basic that we need to learn. I hope I'm clear, right? Shall I proceed? So here I wrote the work done by variable force. But okay, anyways, we have finished, no? So now we'll go to the problems that are based on work done by variable force. Before that, I need to explain what does the graph between, okay, just give me a minute, I'll do one thing. This is spelling correct? Please check. Spelling is correct, huh? Yeah. So we'll try to understand what does the graph between force and displacement represent. Okay. So if you observe, if I take force here and displacement here, okay, let us say I have a shape like this being attained. Now, if I drop a perpendicular from here and if I drop a perpendicular from here, okay, so I'm taking a small portion in this, which I will call it as, I'll call the small portion as ds. So what did I tell you when I discussed about the variable force? When you talk about a variable force, that force F that you're applying no, can be considered to be a constant for a small displacement of ds. So what is going to happen here? Work done by the force for a smaller displacement dw is equal to F into ds. And when you want to calculate the work done, you integrate F with ds from where to where? From S1 to S2. Makes sense? Right. Now, the question is, whenever you're doing a definite integral, what is it actually going to give us? What is the significance of definite integral? It is going to give us the area made by the graph with independent axis. So area made by the graph with independent axis. So what I'm trying to tell you here is, whenever there is a question that is based on force and displacement, and if you are asked to calculate the area under that graph, what are you actually calculating? You're actually calculating work done. So work done by whom? Work done by that force. Is the point clear? Clear with that? Yes. So just make a quick note of this. So let me know once you're done. Let's try this problem. So let's see the problems that are based on work done by a variable force. Okay. The first question says, a body moves from point A to B under the action of a force varying in magnitude as shown in the figure. Okay, it is varying in magnitude as shown in the figure. What is the meaning of it? From A to P, the force is constant. Are you able to understand it? When force is constant, it will be parallel to the x-axis. So A to P, it is constant, and from P to Q, it is increasing, and from Q to B, it is decreasing, right? So it is decreasing in terms of magnitude, and there is a reversal of direction also. See here between Q to R, it is decreasing in terms of magnitude, but from R to B, what is happening? The nature is changing. Because here the force is positive, here the force is negative. How did I conclude that? Because it is above y-axis and, sorry, it is above x-axis and below x-axis. I hope you're able to analyze it. Now, what are they expecting? Obtain the work done, where force is expressed in terms of Newton and the displacement is expressed in terms of meter. So what is that we need to do? All that you need to do is calculate these areas. So all that you need to do is calculate the area. So work done between the points A to P is equal to how much? Force into displacement. Force is how much? 10 into displacement is how much? 2 minus 1. So here it is 1. So force is 10 into 1. 10 into 1, which is going to be 10 joule itself. Clear with that? So what is the work done from P to Q? So work done from P to Q is equal to, you need to calculate the area of this trapezium. So what is the area of the trapezium? Half into base. Base is again 1. So half into base into sum of the parallel sides. This height is 10 and this height is 15. So 10 plus 15 is going to give you 25. Answer will be 25 by 2 joule. Make sense? Right. Similarly, what is the work done from Q to R? So what is the work done from Q to R? It is a triangle, right angle triangle. So it is going to be half into base into, what is the height? 15. Height is 15. So it is going to be 15 by 2 joule. What about the work done from R to B? Half into this is 1 into what is the height? It is minus 15. So it is going to be minus 15 by 2 joule. So when you want to calculate the total work done, all that you need to do is add them. So when you're going to add all these values, it is understood that 15 by 2 and minus 15 by 2 will get cancelled. You're left out with 10 plus 25 by 2. So total work done is equal to 10 plus 25 by 2 is going to be 45 by 2, or it is 22.5 joule. Am I clear with that? That's the answer. Okay. Right. So make a note of this. Why are you not copying? Done, no? Shall I proceed? So this is an NCERT question. I would like you to try it. Do one thing. You understood this problem. Leave some space. Do the next one. So you can copy it in the way I write it there. Problems based on work done by variable force, and problem number 2. Don't write it as 5. When you refer it tomorrow, you will get confused. So a woman pushes a trunk on a railway platform which has a rough surface. She supplies a force of, oh, it has come as 1. I think it is 50 Newton. She supplies a force of 50 Newton over a distance of 10 meters. Thereafter, she gets progressively tired and her applied force reduces linearly with this. Okay, then it can't be 50. Then it should be 100. So 100 Newton over a distance of 10 meters. After that, she is getting tired and the force reduces to half of it, 50 Newton. The total distance by which the trunk has been moved is 20 meters. Plot the force applied by the woman and the frictional force, which is 50 Newton. Calculate the work done by two forces over 20 meters. So try it. Okay. The total distance. So from where to where? Over the total distance of 20 meters. Okay. So in the first case, what is the answer? 1000. In the second case, it is going to be 500. Yeah, tell me. Frictional force of minus 50 is there throughout the journey. Minus 1000, not Newton, Joule. So just want to check one thing. Listen, there is a small correction, not in the problem, in your answer. Listen to this carefully. This is where the tricky part is. So the question is, a woman pushes a trunk on a railway platform which has a rough surface. She supplies a force of 100 Newton over a distance of 10 meter. Means, see, let's assume I start plotting the graph from here onwards. So this is force, this is displacement. A force of how much value is supplied? 100 Newton through a distance of 10 meters. So starting from 0 to 10 meter, there is a constant force. Are you accepting it? So it is parallel to the x-axis. After that, what is happening? She is getting tired, and the force progressively, sorry, the applied force reduces linearly. So the force is reducing linearly till what value? Till a force of 50 Newton. This is 100 Newton. This is 50 Newton. And you drop a perpendicular from here, it will be 20. Makes sense? So what is the mistake that happened is, here you calculated as 1000. Okay. But here it is not 500. The work done is not 500 because here it is a variable force. So for variable force, you need to go with integration, or if you know the graph, you can go with the area under that graph. Right? So what is going to be the area in the first part? That is, what is the area of the rectangle and what is the area of the triangle? What is the area of the rectangle? So work done between 0 to 10 is going to be 100 into 10, which is going to be 1000 joule. What is going to be the work done from 10 to 20? It is half into base, that is 10, into sum of the parallel sides is 100 plus 50. So it is going to be 150. So this will cancel the 75 times. Answer will be 750 joule. So what is the total work done by the force that she applied? So work done between 0 to 20 is not 1500, rather it is going to be 1750 joule. This answer. Got it? Similarly, there is a constant frictional force of 50 Newton always acting on the object. So where should I plot that 50 Newton? Obviously at the bottom, right? There is a constant force of 50 Newton that is acting at the bottom. So what is the work done by the friction in this case? What is the work done by the friction? Friction is equal to, work done by the friction is force into displacement, right? They both are in opposite direction. So it is going to be minus 1000 joule. So it will be minus 1000 joule. Is that point clear? That is the work done by the friction. Right? Calculate the work done by the two forces over the distance, means it is 1750 minus 1000. So total work done is how much? Total work done is equal to 1750 minus 1000, which is going to be 750 joule. That's the answer. Is the point clear? Right. Done with this? Right. A particle moves along the x-axis from x is equal to 0 to x is equal to 5 meter under the influence of a force given by F is equal to 7 minus 2x plus 3x square. Find the work done in this process. So you know the formula, no? What is it? Did you understand whether it is a constant force or a variable force? It's a variable force. So variable force means use integral of F ds from where to where? Yes. See, only difference is now don't stick to the formula. If they have given s in the problem, write it as ds. If they have given x, write it as dx. Okay, s or x can be used for displacement.
But it can just be an equation. Will it just be an equation?
You want me? The equation is here, no?
No. The work done isn't just an equation.
Because the numbers are given, no, 0 to 5.
Oh, okay.
Whenever you do definite integration, you will not get an equation. You will get a
Yeah,
number.
okay.
Yes. I don't know what is the answer, but what is it you got? Is it raining? Suddenly. Is it raining?
Yes, sir.
All of a sudden. It was nice only, no? Okay. So what is the answer? Anybody else? Those have got the number? Yeah. So what will you get? Integral of 7 is 7x. Did you write that? So 7 into 5, 35, minus 2 into x square by 2, 25. Minus 25. Minus 35 minus 25 is 10. Plus 3 into x cube by 3. So 5 cube is 125. 125 plus 10. 135 should be the answer. So listen. So a particle moves along the x-axis from x is equal to 0 to x is equal to 5 meter under the influence of the force given by this value. It is 7 minus 2x plus 3x square. Obviously, it is understood that it is a variable force, right? So find the work done in the process. So whenever you have the variable force, W is equal to integral of F into dx, where in this case, x is varying from 0 to 5. So what is the value of F? So integral of 7 minus 2x plus 3x square times dx between 0 to 5. So what will you get? So I'm doing it directly. 7 into integral of dx is 7x minus 2 into integral of x is x square by 2 plus 3 into integral of x square is x cube by 3 between 0 to 5. So 2 and 2 will get cancelled, 3 and 3 will get cancelled here. Substitute the upper limit, that is 7 into 5 is 35 minus 5 square is 25 plus 5 cube is 125 minus everywhere you are going to substitute 0, it is going to be a 0. So answer will be 35 minus 25 is 10 plus 125 is 135 Joule. I hope it is clear, right? So with that, we come to an end of work done by a variable force also. So I hope the problems have got registered in your mind, right? So the next set that we are supposed to discuss is what is energy, right? So what does energy mean? Energy is basically the capacity or ability to do work. I told you, no? If you have to do some work, all that you need is energy, right? So what does energy speak about? It is the capacity or ability to do work. The energy of an object is measured by the amount of work the object can perform, right? So to put it simple, right, if at all you want to calculate the energy possessed by a system, all that you need to do is calculate the work done. That's it. Okay, that is why they both are related concepts. So what did we say? Energy is the capacity or ability to do work, and energy is measured by the amount of work that can be performed by a particular object, right? Therefore, what can you conclude? For you to calculate the energy, all that you need to calculate is work done. So if you're able to calculate the work done, we'll say that this is the value of energy that will get stored as. But the only difference here that you need to make a note is, when you talk about work done can be of three types. What is it? It can be positive, negative, or zero. Whereas when you talk about energy, energy is never negative. It is always positive, right? It can be zero also. If the work done is zero, energy stored is also going to be zero. But it can never be negative. So work done can be positive or zero. Is that clear? So whenever there is a question where they're asking you to calculate energy, if a negative value is given, it does not make sense at all. Was that point clear? Yeah. So when we try to classify the energy into different types, right? What are all the types of energy that you already know? So first you can think of kinetic energy. So what do you mean by kinetic energy? So energy possessed by a body by virtue of its motion, right? So if I take an object of mass m, just put it into motion, right? You can define a parameter called as kinetic energy associated with it. Am I clear? So I just want to ask you one question. Can you tell me, if an object has mass and it has velocity, what are the two important physical quantities that can be measured? If an object has mass and velocity, what are the two important physical quantities?
Momentum.
Linear momentum and kinetic energy. That is why they both are very much related concepts. Am I clear? So whenever you see an object having mass m and velocity v, by default, you should understand the fact that the object has both linear momentum and kinetic energy. So you can use any of the parameters and they both are interrelated. In this chapter, we'll see how they both are interrelated. Okay, but I want this point to get registered in your mind. So the energy possessed by body by virtue of its motion is called its kinetic energy, right? A moving object can do work. A moving object can do work. The amount of work that a moving object can do before coming to rest is equal to its kinetic energy. So this is another way of understanding it. Because what did we say? Energy is a capacity to do work. So what are we trying to say here is, the energy possessed by body by virtue of its motion is defined as kinetic energy, accepted. But an object in motion can do some work. So the amount of work that is done by the object even before it comes to rest is what is called as kinetic energy. Right? Now, the question is, if I take an object of mass m, which has an initial velocity u, and let's say it started moving through a displacement of s, it has attained velocity v. Are you able to understand this? Let's say it is moving under the influence of a constant force. What is happening? It is moving under the influence of a constant force, right? Now, what I'm going to calculate is, what is the amount of work that is done by that constant force which I'm talking about? So, amount of work done by the constant force is going to be force into displacement, at least in this scenario, because you can understand that the velocity is changing in this direction. So, force is applied in this direction. I'm only interested to calculate what is the work done by the force that is acting in the direction of velocity. Am I clear? Am I making sense? Right. Now listen to this. But what is force according to Newton's second law? Force is mass into acceleration, and displacement is going to be displacement. So here, if you observe, actually it should have been cos 0. I didn't write it. So it is F into S. So can I write this as M into, using VU, can I write V square minus U square is equal to 2AS, or A is equal to V square minus U square divided by 2S? So take this and substitute it here. V square minus U square divided by 2S into S. S and S will get cancelled, right? This will come out to be half of mv square minus half of mu square. That is why this half of mv square is what is given as the mathematical formula for kinetic energy. So where does that kinetic energy actually come from? What did I actually start with? I didn't start with the definition of kinetic energy. I started with work done. But work done gave me the mathematical formula for kinetic energy. So if somebody asks you, how did you know that half mv square? Why can't it be 1 by 3 mv square? It could have been, no, but it is half mv square because of this reason, right? So what is happening here? The work done here, is it not coming out as the difference of the kinetic energies? So half mv square, if I call it as kinetic energy, I'll call this as final kinetic energy. I'll call this as the initial kinetic energy. Final minus initial should give you the change. So work done, can I call it as change in kinetic energy? Can I? So work done is actually equal to change in kinetic energy of the system. And this is given a name called as, work energy theorem. It's called as work energy theorem. No, this mathematical expression. Whatever work is being done is equal to change in kinetic energy is said to be the statement for this theorem. Means what it is stating is, whatever work you're going to do, when I say work, no, work done by all the forces is equal to, will always reflect as a change in kinetic energy. Change in kinetic energy. And this mathematical expression is given a name called as work energy theorem. And this is a very, very, very important one. Right? So with just this theorem, you can solve most of the problems in physics. It's not related only to this chapter. In other chapters also you can solve. Is the point clear? So just make a note of it. Clear with this? Yes. What is change in? I didn't understand. I'm saying kinetic energy and linear momentum can be related. Okay. Am I clear with this? Okay, listen to this. So we'll wind up with this for today. One important announcement, tomorrow I have a workshop in one of the schools, so I'll not be able to come back on time. So that is why what I've done is I've scheduled a substitute teacher for tomorrow alone, but it will be an online class. Okay, please cooperate with him, and I'll ask him to continue with the rest of the chapters and ask him to solve problems so that tomorrow's class is not wasted. Is it clear? So I'll try to give problems based on work energy theorem. One more thing that needs to be explained is, listen to this. Whatever I've derived here is the relation between work done and the kinetic energy for a constant force. But you can derive the same expression for a variable force also. That, see, both are same. It will give you the same expression and same work energy theorem, but the only difference is that derivation is generally asked as a 2-mark derivation in your exam. I'm talking about the exam perspective, it is important, but conceptually it is the same. Okay. And one important point is this expression, as I told you, can be used to solve any problem in physics. Okay. So tomorrow I'll ask them to solve problems based on this one and energy conservation theorem. So these two things will be taught tomorrow. So this work energy theorem has nothing to do with variable or constant force. It is same. Am I clear? So tomorrow it will be an online class, and I have already told you what are the topics, so he will discuss. Okay, but only request is please cooperate and respond. Okay, don't be silent. The other teacher will lose the interest to teach you. Okay, last week also I observed most of the class was silent. Only 2 or 3 were responding. That will not create interest, right? So please speak out. Those are online. Am I clear?
Yes, sir.
Yes, sir.
Okay, I'll see you guys. So we can start the math class around 6:15.
Thank you, sir.
Yeah.